Hello. Thanks for coming, everyone. I'm talking about open source industrial control. Caw-caw! If you're as tired as I am, I hope you needed that. All right. My name's Jacob. I'm an electrical engineer at the U.S. Bureau of Reclamation. We manage water in the West, 17 western states. It's very dry. We have about 600 dams, reservoirs, 53 hydropower plants, 250 rotating machines within our fleet. I design and build cyber-physical systems. To me, a cyber-physical system is any time a computer can flop a bit and have some causal effect in the world around us. So this can be as complex as your social media feed getting you to buy something, or just a computer-controlled relay turning on your light in the living room. Here's some contact info. That'll be at the end as well. So today I'm going to be talking about rotating machines. So something to know about a rotating machine, there's two parts. There's a rotating part. This is called the rotor, rotating rotor. There's a stationary part. It's called the stator, stationary, stator. This is the rotor. It's being crane lifted back into the bore. This is one of our largest machines. For scale, those two humans, this is 2,800 tons of rotating mass. This can produce upwards of $1 million a day in revenue, depending on peak spot prices of electricity. So the basics of a rotating machine, it's really just a magnet moving past a loop of wire. So we produce current into this rotor, and we produce an electromagnet. So we have north-south poles. And then that spins around in the bore, and on the stator, we have three windings. In the US, we have a three-phase system. So three windings create three phases. We have a red, blue, and green phase, and these just have loops of wire for these magnets to spin past. It's often the case, so when these things are online, they're spinning very fast. They're at synchronous speed, so 60 hertz, depending on how many magnetic poles are on the rotor. But there's often cases when we want to spin them slowly and precisely to do various testing and maintenance tasks. So I call this slow roll testing, and various reasons we need to do it. One is bearing alignment. So the diagram in this machine, it has 3 oil slick bearings. And to align those, typically what we do is turn the machine 90 degrees, make some measurements, do some tweaks, turn it 90 more, iterate on those measurements and tweaks until we have all 3 bearings aligned. So that takes precise, slow control of the machine. Signal mapping is also a case where we want to slow roll. And so this is where we fit the rotating part with some type of sensor, and we monitor the signal off this sensor. So this could be a camera, and we can map the camera's position, and we can get physical condition mapped to a location inside the machine. And there's other types of sensors that I'll talk about in a sec. So how do we rotate these machines slowly and precisely? Well, we used to put people inside, and they would push it. And as you can imagine, that's pretty cumbersome. It's not very safe. It takes days of planning, lots of radio communication with who's in, who's out of the machine. And there's a lot of rotating mass. It doesn't stop for mere humans. So how can we get better? Well, I think it was Archimedes that said, give me a relay contact and I can move the world. And so that's what we're going to do. So if you've ever worked with a DC stepper motor, that's what I've done here. I've turned these giant machines into a DC stepper motor. So a DC stepper motor, all you're doing is applying current to create electromagnets in such a way that the rotor will turn to that electromagnet. Then you move the electromagnet and it turns again. And you have these discrete steps that form a continuous rotation. So that's what I do. This is a cartoon of a rotor. It's an iron core wrapped with wire. We put current into that wire and we make magnetic fields. So we have north-south poles on the rotor. This is the spinning part. Then we have the red phase, the blue phase, and the green phase of our 3-phase machine. I can then apply current to the red phase, say, and I produce magnets in the stator winding, north-south. Opposite poles attract. However, the rotor's already aligned with the red phase in this case. So opposite poles attract, my force is radially outward in this case. There's no torque, nothing turns. If I was to reverse the current direction, North poles become south poles. Like poles repel. Now my force is radially inward. Again, no torque, no movement. However, if I picked another phase that wasn't aligned, I can apply current and get those same north-souths, opposite poles attract. My torque in this case is counterclockwise, and I get rotation until I'm lined up with the green phase. Similarly, I can tweak my current, change the direction, norths become souths, souths become norths. Now my torque is in the clockwise direction, and I can get rotation until I'm lined up with the green phase. And this is how I turn these giant machines into DC stepper motors. So what does this look like in reality? So here's a prototype that we built in 2020. Here's me with the prototype. It has a small power supply. This is what we put on the rotor to set up those electromagnets that we want to align. This is a larger power supply. This is what we switch for controlling the phases on the stator. It has a current reverser. This takes that one directional DC current supply and allows me to switch direction of the current. And then there's a physical switch system. This is physical potentiometers and switches. There's some drawbacks to this prototype. So this was literally me standing over a machine. I removed covers, and I would stand over the machine and look at poles as I switched it. And I would say, okay, pole align, unalign, align, unalign. And it's very specialized and hard to use, right? You need to know about the machine. You need to know how the machine's wired. You need to know about electromagnetism. This isn't very accessible to the average plant personnel. There's only visual positioning in this case. So remember, I needed to turn exactly 90 to align those bearings. Well, if I have a 16-pole machine, I can count 4 poles. That's roughly 90 degrees. But is it 90.000 degrees? I don't know. It's not very modular. That large power supply weighs almost as much as I do, and it's very difficult to get into places where I need it to be inside the machine. So there's a better way, and my way is Python and Raspberry Pi with some other tech like WebSockets, Flask, Celery, I2C, Redis, and I'll get into that. So I built a browser application, and here's why. Here's some reasons. So I also work on SCADA engineering. So SCADA stands for Supervisory Control and Data Acquisition, and we typically use what's called a PLC, Programmable Logic Controller. And when you program a programmable logic controller, you usually use visual programming called ladder logic. And these ladder logic files create binaries that are very hard to version track in a human-readable way. Well, now my web application's tech stack is all plain text. I can use great continuous integration tools. I can version track it in a human-readable way. Other benefits, the client doesn't have to install anything. So I work for the government. Government-furnished machines are hard to install software on. You need to get tons of approval. But hey, they all connect to a network and they all have a browser. That's all I need. Reduced training. Everyone's used a browser. We all know what a button looks like. We know if we click it, it does something. And it's proven. Tons of money backs this technology. Bugs are somewhat rare. This is proven technology. It's used all the time. Interactive visualization. So the technology of the internet was built to deliver interactive, rich visual content, and that's what I need to do. Support. So SCADA engineering is kind of a rare niche field, but the most recent Stack Overflow survey shows the top 3 languages are the languages of the internet. So it's fairly easy to hire a dev in this tech stack. Scalable. So I'll show you how I'm using Celery for scalability and extensibility. Some of the cons, it's not truly real time. So if I was building a system that was doing event confirmation to say set off your airbags in your car, I'd want a truly real-time system that had bound latency, right? Controlled and bound latency. That's not the case here, but honestly, I don't care. I don't care if the OS is off prioritizing something else for a millisecond. I don't care if Python's garbage collecting. That's not going to affect me that much. Milliseconds don't matter to me. Security. So I fully air gap this. It's not touching the internet. I just take the technology of the internet on my own little island. And so here's what it looks like. I made a bunch of Pelican cases. These can all fit on a pallet. I can freight ship them to a power plant, fly out there and meet it there and use it. So how does this work? So I have what's called the distribution box. This distributes power through my system. So remember, there's the rotor and the stator. So I need to distribute power to both the rotor and stator parts of the system. So I plug this into the 480 volt plug, right? You all have 480 volts at your house? No, but the power plant has lots of 480. We're usually running everything on 480. It actually probably has more 480 plugs than 120 volt, what you're used to. And so this distributes that 480, so I can have one power supply. Remember, I'm injecting current on the rotor, and I'm injecting current on the stator. And so I can have at least one power supply on the rotor and at least one on the stator, and I can have up to one on the rotor, or up to 4 on the rotor and up to 4 on the stator. And so it's scalable in hardware as well, modular and scalable in hardware. Then I have control boxes. So there's a 480 to 120 volt transformer in my distribution boxes. And so that makes a 120 volt plug that I can power my control boxes off of. Each of these control boxes has a Raspberry Pi inside. And then I communicate with all the power supplies with something called PM bus, power management bus. It's basically just I2C with specific commands for controlling power supplies. I use the SMBus2 library to do this. Then I need to route current, right? I need to inject current. So I parallel all these power supplies together, route them through my control boxes, and put them in where I need to put them in. So for the rotor box, it goes to the rotor and makes magnets. Then I have some sensors that I'll talk about later. I make my own LAN, my wireless LAN. The stator talks to the rotor box through that wireless LAN, and then the stator box can control which phase it's going to. So it can get one of 2 phases. Remember, it's a 3-phase system in the US, so I'm picking control of 2 of those 3 phases. So I select one of the 2 of 3 phases. So when I build these systems, I like to source my components off of places like McMaster-Carr or Automation Direct, specifically because they provide CAD drawings for almost everything they sell. So I can download those CAD drawings, throw them into a CAD image where I can see if it's going to fit in my Pelican case. So the red outline is the Pelican case. Here's making the faceplate. So I made sure everything could lay out, all my holes where they need to be before I went and got it CNC'd and put everything together. And then everything is bolted to that faceplate, so I can pull it out of the Pelican case and work on everything, turn it upside down on the workbench, work on everything. Here's the Raspberry Pi CM4, here's some DACs, here's some custom PCBs I made. So how does this work? Multiple Raspberry Pis, this is a distributed computing architecture. So the rotor control box is the brain, it's the conductor of the orchestra. So it detects event requests. These event requests are coming from the user in the browser or a sensor. A sensor signal starts an event, and if a certain event happens, it sends a task to a message broker. The stator, all the stator is doing is running a celery worker. That's it. And it has some tasks defined on it. So it's just connected to the Redis instance on the rotor controller, listening for tasks in a queue it was assigned. It monitors that queue for tasks, and when it sees one, it says, hey, I know that task's for me. I'm going to go carry it out. And so this is extremely scalable. So if I want to make another box that does something else, maybe some specific type of sensor, all it needs to do is have another celery worker and its tasks defined on it, and then it just connects and does its tasks as it's commanded to. So let's run through an example of how this works. So here's the front end. It's on my government furnished iPhone screenshot. So first I press this scan button, and it's kind of small, but I see four power supplies are connected. I slide my slider all the way up to turn the power all the way up. And once I've selected those power supplies, I can now start moving the rotor. So I go to the turning page, and I select which lead. Remember, I can choose 2 of my 3 phases. So I select a lead out of a drop-down, and then I press the forward button. Now remember, I'm fully air-gapped, so on the front end in the HTML, I need to host everything. So the Socket.io library is hosted on my machine. I can't go to a CDN, a content delivery network, out on the internet to get the Socket.io library, right? Of course, there's a forward button. Then in JavaScript, I grab that forward button and I trigger an event, in this case on touch start. So when I touch that button, the current on function's called. In the current on function, I style the front end. So I light up the button and I turn on the request light. Hey, I requested forward. Then I emit to the back end. On the back end, of course, there's something to detect that. This is the rotor box. It's the server. So if a lead, which phase you wanted to do, which direction, forward or reverse, and how much current you want was provided, then it says, hey, okay, I'm going to send a task to the message broker. Then back on the stator, you see this Celery log. Hey, I got this task. And then it says, oh, I know what that task is. I've been given a lead, a direction, and an amount, and I'm going to fire an SCR, and I'll get into what that means. So essentially, this is just turning on a GPIO pin on the Raspberry Pi. That GPIO pin turns on a relay. That relay activates a custom PCB. This custom PCB just puts that relay signal to an opto relay. That opto relay puts 24 volts to the primary side of a pulse transformer. That pulse transformer pulses that 24 volts through a 555 timer, and that pulses the output to the gate of the SCR. So what is an SCR? Well, an SCR are these little brick things. It stands for silicon controlled rectifier. You can think of it just as a high current transistor. It's technically a 4-layer silicon device, but for the purposes of this talk, it's a high current transistor. And so this brick actually has 2 SCRs in it. And so I use 4 of them for a total of 8 SCRs. And if I turn on these 2 SCRs, then I can route current in this way. And so see that I have current in this direction through this stator phase. If instead I was to turn on these 2 SCRs, the routing of current is different, and I have current in this direction through that same stator phase. So same way, I can use the other 2 SCRs to do the same thing with the other phase. And so now that the SCRs are being gated, I can turn on my current supplies because the gate is open, right? So I use SMBus2 to talk I2C to my power supply, say, hey, turn on with the amount of current that was requested. And if all that happens without any exception handling triggered, then I emit back to the back end. And something interesting, remember, this is on the stator box. The stator box is not running the Flask app. All it has is a Celery worker. So this emit is not actually happening from the stator. It's putting a message back to the rotor and saying, hey, put this in your message queue, and the Flask app is listening to Redis and is saying, oh, hey, look, I need to emit. So it emits back to the front end, and the front end JavaScript detects that emit, and it styles the confirm button. So, hey, the power supplies did indeed turn on. And then back on my scan, I see that, yes, indeed, all 4 power supplies turned on. So so far, all I've done is mimic the analog physical switches with software. Is that better? I don't know, I think it is. Some people might not. But I can do better. So we bring in some sensors. Specifically, this is called a once per revolution. It's really just a laser pulse. So when this reflector goes by the little laser dot here, it pulses. And this reflector goes around once per revolution. It's taped to the shaft of the machine. And so once per revolution, I see a laser pulse, right? That'll be important in a sec. Then I use a rotary encoder. So this is an 8-bit gray code rotary encoder. Gray code's pretty sweet because for every consecutive count in gray code, only 1 bit changes. So you can error detect with this. Because if 2 bits change for 1 click in the decoder, that's an error, right? And then something interesting too, this wheel on the encoder, the little black wheel here. So in the textile industry and print industry, you want to measure reams of material coming out of a machine. And so these wheels have very precise circumferences for measuring these things. So I had to machine a shaft to stick this wheel onto the encoder, and it's driven off part of the machine, this part on the shaft. It's called a slip ring. This slip ring, remember, we have 250 machines in our fleet, probably more actually, they're all different. I don't know the circumference of that slip ring. I can measure it with a tape measure, but there's all kinds of stuff in the way. It's called brush gear. It's how you get current onto the rotor. So tape measures are kind of out, and I'll get to how we do this, but I need to learn that drive ratio, and measuring isn't an option. Even if I could measure, any error in that measurement's gonna propagate, right? So if I'm an inch off, I'm measuring that slip ring. If I go one rotation around, I'm now more off, and more and more and more. It compounds, right? So how do I deal with this? Well, first I need to read those sensors. I use what's called an MCC DAC hat. This is a hat that sticks on the GPIO header of the Raspberry Pi and gives you extra functionality. It's made by Digilent. This one has, they have various DAC hats. This one has 8 digital I/O channels. You can stack up to 8 of them on the same Raspberry Pi. And of course, they have an API in Python. You can learn more about it there. It's called DAC hats. I'll give you a moment to snap some photos. You can also just come to me and I'll tell you all about it. So yeah, and then, so that's how I get the sensors. And then I need to have a calibration procedure. So on the front end, I built this oscilloscope. It's a real-time oscilloscope. It's all written in JavaScript. But the important thing here is that these red lines are the once per rev signal. The green line is the evolution of the turning process. So as soon as I hit the first red line, I say, okay, my rotation started. Now I'm gonna track that rotary encoder until I see the second red line. And I saw 4,168.125 degrees. That's how much the encoder turned for one revolution of the rotor. So I know the drive ratio, right? For every 360 degrees the rotor turns, the encoder on this particular machine turns 4,168.125 degrees. There's my drive ratio. So I call this mapping, and the reason I call it mapping is because if I know the pole count of the rotor, I can now make a map and say, for example, just making up numbers, say click 473 of the encoder needs to be forward on green phase to get clockwise rotation, right? I can build that map now. And I can store that map in a database for later recall on that particular machine in the asset. And so future work. So I want to take this and do automation. So like I said, from that map. So continuous rotation is easy. That's trivial. So it's like a thermostat. If you're above a certain speed, turn off the gas, right? don't move. If you're below that certain speed, apply, right? And so it's like a thermostat, and you're in continuous rotation between some low speed and some high speed. Turning and parking is going to be much more difficult because the moment of inertia for each of these machines is totally different. Friction's totally different. If I give the same amount of current to machine X as I do to machine Y, it might turn more than the other machine, right? And so that's going to be very difficult to figure out. I don't think impossible. It's going to be fun. We'll see. Another thing I want to do is approximate circumference so that I can automate that calibration process. So I've invented this tool. It determines circumference from D and L, and then you can determine the radius and then circumference from those values using geometry. So I propose making a very precisely machined jig and putting a high precision laser distance measurement device on it and sliding that along the jig while measuring to get L. The reason I want to slide it along the jig is if I tried to place it exactly in the center of the jig, inaccuracy in hardware and stuff is gonna not place it exactly in the center and I'll be off. If I slide it along while measuring, all I need is that extrema and I have exactly L, exactly the midpoint of D. I can get the approximate circumference, plug that in, and automate the process of calibration with that approximate circumference. There's something called partial discharge mapping. In previous research, so partial discharge, so the stator winding typically runs at like 13,000 volts. That needs to be insulated, so it's copper with insulation around it. That insulation is made from epoxy and mica layers, and that epoxy during production has micro bubbles in it. And when it's exposed to high voltage, those micro bubbles ionize. That ionization happens 120 times a second, right? 60 hertz, negative half cycle, positive half cycle. So it ionizes on the negative half cycle, ionizes on the positive half cycle, 120 times a second. And that ionization eats away at that bubble, and it eats away at the insulation over years. So we need to trend that. So I discovered that using the NFC antenna found in your common phone can detect this signal across the air gap of the machine. So I slap that NFC antenna on one of the rotor poles, and I measure partial discharge, and I can say, hey, look at around slot 200. So the stator has copper, iron, copper, iron, copper, iron to make that copper winding. And so it's slots. Every copper is called a slot. And so around slot 200 and around slot 60, I have high PD count. I can trend that. Is it increasing? Is it staying the same? And I can advise asset managers, hey, you can do a local repair or you need to do a bulk repair. And that's millions of dollars or thousands of dollars, right? So, and outage times as well. There's more information at that QR code, but that's one application of this, right? I would build a box that takes tasks from Celery and partial discharge maps. Air gap measurement. So again, there's a spinning part and a stationary part, and between them is about an inch. So if this changes, magnetic force changes with distance. So if the air gap is changing around the circumference of the machine, you get cyclic forcing. And if the cyclic forcing is big enough, you can rip the machine apart. We don't want that. So we often do tests to determine the shape of the machine. Is it circular? Is the air gap changing around the circumference? And that's taking a proximity probe, slapping it on the rotor pole face. And what a proximity probe does is measures the voltage for grounded iron. So it sees iron, copper, iron, copper. And the signal makes it look like it's close, far, close, far. So but previously, I would post-process that data back in the office and use a peak detection algorithm and count how many slots, how many peaks I see. That's one rotation, get the shape from those peaks. But now with that rotary encoder, I can do this in real time, which is pretty cool. So to conclude, the line between information technology and operational technology is blurring. Asset managers want real-time insight into the condition of their machines. Subject matter experts want real-time insight into their sensor signals so they can advise the asset managers better. Operators want smarter automation. We want to centralize data to train learning models and make predictions. And this is all to say that this type of tech stack melded with the traditional SCADA PLC tech stack is how I think we're going to achieve that in the future. And this is just an example of some of that. So with that, I have about 2 minutes for questions. There's my contact info. I'm co-hosting an open space tomorrow, 10 a.m., room 316, if anyone has more questions. Also, probably like most of us, I'm not really one to start conversations, but I'm totally happy to talk. So if you see me in the halls and want to know more, just tap me on the shoulder. I'd be happy to talk more about this or anything else. So yeah, thank you for coming.
I just want to say, first of all, extremely awesome work and presentation. I think it's a little different kind of thing. I used to live out west near the Columbia River, and so I know that personally I visited Grand Coulee.
Yeah,
and the
Grand Coulee. That machine was.
Oh, that was Grand Coulee?
Yeah, third powerhouse. Yep.
Yeah, so there's huge machines, very important to the region and probably nationally. So very cool. I guess in terms of question. To what extent was there support or resistance, organizational? These are large government entities. They're not super on nimble. Let's just pull up a new library. Yeah, just download it. It's fine.
So support is zero. So I had to write a grant, and I'm the only one on this project. So I wrote all the software, built all the boxes, designed everything. So and I'm trying to show value, and they're seeing it now that it's built, and so now regions are, thanks. So Regions and facilities are now buying them. They say, hey, I want a test set. Can you build me one now? And I'm applying for more funding for facilitated adoption throughout reclamation. So yeah.
Cool. Well, kudos on the work. It's very cool. Yeah.
Thank you. Thank you.
Hey, so how much has like the thinking or the priorities changed since Stuxnet in your industry?
For,
Like
Stuxnet?
yeah, like how has the thinking changed, or like are people more open to?
Yeah, no. Well, so yeah, Stuxnet was a huge thing. It's really fascinating, in my opinion. But like, most our stuff is, yeah, and Stuxnet even was like an insider threat, right? So, or how it propagated first. Patient Zero, I guess, was an insider that plugged the wrong thing in. They unknowingly plugged the wrong thing in. But yeah, I don't know. That's a good question. It's not
Not top
necessarily on my radar. We definitely make our systems incredibly secure, and most of that security is from air gap. But yeah, good question.
As everyone clearly is acknowledging, that was an amazing presentation. What safety mechanisms do you have to put in? Because like if something goes wrong with that, you could presumably have like an out of control
Yeah, you'd think so.
runaway process.
Great question. There's really no safety concerns as long as no one's inside the machine. So all 8 power supplies is about 40 kilowatts. That's about 40 toaster ovens. And so the amount of power that machine sees 24/7, 365 is hundreds of times that. I'm not going to damage anything if it like puts the wrong direction of current in or something, right? There's no question about that. So yeah, and again, we just red tape off the machine so no one gets inside, and we should be good. Yeah, but again, like if this was a critical system, I probably wouldn't be using this tech stack solely for, that. I'd probably be using a PLC, yeah. Great question. Are there any others? Awesome, thank you.